So again, it's Introduction to Computer Organization. Okay, so what is computer architecture? So it is the study of computers. So computer architecture, it's the view of a computer as presented to software designers. Computer organization is the actual implementation of a computer in a hardware. So what is a computer? It might be a desktop, a netbook or a laptop, mobile phones, iPad. So a computer is a general purpose device that can be programmed to process information and yield meaningful results. So how does it work? How does computer works? So through the computer composes of a program and information store that provides results. Now, the program is a list of instructions given to a computer. And the information store data, images, files, and video. Computer process the information stored according to the instructions in the program. So what does a system unit looks like? Okay, so if you're going to open your system unit, the main composition of this one is of course the CPU and the memory and the hard disk. Now, memory stores the programs and data. So basically, when you turn off your computer, it does not stores the data inside it, while the hard disk stores programs or data permanently. So let us make it a full system. So you have your computer, you have your system unit, you have your memory, you have your hard disk, and of course, the system unit will not work without the what? Input and output devices. What are the input and output devices? The input devices are, we have the keyboard, we have the mouse. The output devices are, we have the monitor, we have the printer. So computer system. A computer system is a particular type of system that its primary purpose is that of performing computations. Before the time of electronic computers, a computer was a person that performed computation. Okay? So, again, when you say a system, it doesn't mean this is a machine. It might be a process, a procedure, or a certain person. Now, a computer system is composed of a central processing unit or the CPU that has control unit or the CU. We have the ALU or the arithmetic logic unit. We have the memory and the input-output subsystem. Okay, computer system overview as perceived by the von Neumann architecture. Okay, I think you're familiar with this illustration. We have the memory. The CPU contains the ALU and the CU or the control unit. And of course, the I/O devices. Let's try to look at the process inside the von Neumann architecture. Okay, so the von Neumann model, these program computers have the following characteristics. So the three hardware systems are CPU, main memory system, and the I/O system. The capacity to carry out sequential instruction processing, a single data path between the CPU and main memory. The single path is known the von Neumann bottleneck. So trying to look at the von Neumann model or architecture, this is the general depiction of the von Neumann system. These computers employ a fetch, decode, execute cycle to run program as follows. So again, for the von Neumann model or architecture, the cycle of the model is fetch, decode, and execute. So the central processing unit that contains the ALU and the CU, okay, as you can see on the screen. Okay, the control unit here fetches the next instruction from the main memory, using the program counter to determine where the instruction is located. The instruction is decoded into a language that the ALU can understand. Okay? Any data operands required to execute the instruction are fetched from memory and placed into registers within the CPU. The ALU executes the instruction and places result in registers or memory. Okay, arithmetic and logic unit. The ALU performs the arithmetic operations as well as the logical operations. So arithmetic operations include addition, subtraction, multiplication, and division. While the logical operations are the greater than, less than, equal to, okay? Then these operations are normally carried out with registers that are part of the CPU. So when you say arithmetic logic unit, operations are addition, subtraction, multiplication, and division. And the logic unit or the logical operations would be the greater than, the less than, and equal to. So storage or memory. The storage subsystem is a unit that is capable of retrieving and saving instruction as well as data. There are two main types of storage. We have the primary and the secondary storage. The primary storage is the memory that is immediately available to the CPU and it is normally fast, okay? Which is the random access memory or RAM. Secondary storage is indirectly available to the CPU and it is typically slower, which is of course the hard disk or tapes. Okay, input-output. The I/O subsystem is critical since it is the one responsible for receiving and sending data to the outside world. The computer would be useless to us without this system. There are many devices that can be used for input and output. So typical input devices, we have the keyboard, we have the mouse, graphics tablet. Typical output devices are screens or the monitor and force feedback joysticks. Okay? So number systems. Of course, if we are talking about the computer, we have to know and we have to be familiar about the number system. Okay? So everything that the computer handles is stored in the form of numbers. The numbers are meaningless by themselves if we need to associate significance so that they can be useful. We associate symbols with the concept of a number, and for example, the number 3 is represented with the symbol 3. The symbol is not the number 3, but a placeholder for its concept. So decimal number system. We use the decimal number system in our daily lives if you want to count. Okay, you know your cell phone number, that's decimal number system. It is called the decimal system because we use 10 distinct symbols. The 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we can represent any number by combining these symbols. The number 3,748,321 can be represented with 3748321. So the decimal number system are the number system that we use daily. Okay? So decimal numbers in computers. If we want computer to use the decimal number, we need to have devices of storing the 3B and manipulating 10 values of primitive symbol. Although possible, this system would be subject to error and deterioration and would imply a short lifetime. Now, as you can remember, class, of course, if we are going to use the computer and we're going to input from the keyboard, we of course in our own language, in the human language, we understand that 1 is 1. We understand that 2 is 2. We understand that 3 is 3. But what about the computer? Can the computer read? Can the computer actually read number 3, number 4, number 5, number 6? No. Why? Because what the computer understands is what? The binary language or the machine language. So meaning to say, these keys from the keyboard, like the 1, 2, 3, 4, 5, 6, 7, 8, and 9, they have to be converted into the ASCII codes, and then the ASCII codes are converted into binary language. And the binary language is the machine language or the computer language that the computer understands. Okay? Binary number system, as I mentioned earlier, what is the simplest number system we could use? We could use the unary number system, but it does not lend itself to simple and speedy manipulation in terms of arithmetic and other operation. We use the binary number system inside the computers. The system only has two symbols, which is 0 and 1. Okay? So when you say binary, the only two symbols involved are the zeros and 1. Okay? So binary number system in computers, beside the physical reasons for using binary, there are also mathematical advantages. Boolean algebra is an area of mathematics that studies the properties of the binary system. It provides us with an excellent foundation not only to design the electronic parts of a computer, but also to develop algorithms to expedite computation. So these are the examples of the binary. If you are familiar with the, we have the binary here, we have the hexa, okay? So I think we're going to discuss the computation of binary in the next meeting, actually. Since the topic today is about introduction. Coding information. We usually assign meaning to different symbols. As long as we agree on what symbol has what meaning, we are able to communicate with each other using those symbols. We can use 0 and 1 in place of no and yes. We can use 0 and 1 for true or false, like the Boolean, okay? They could also mean close and open. They could also mean agree and disagree. They could also mean bad and good. Coding text. One of the very useful coding schemes we use with computers is the coding of text characters. The ASCII code is widely used throughout the computing world. Every character has a binary code, and we can represent text by using binary numbers and interpreting them as characters. ASCII is a subset of Unicode, which is used to encode international symbols. So, as I mentioned a while ago, for example, in our keys, we have the 1, 2, 3, 4, 5, 6, 7, 8, 9, or the 0. We also have the A, B, C, D, E, F. We also have the symbols of period, comma, question mark. Now, these keys from the keyboard is translated into ASCII. That's how the computer understands the keys, okay? So, for example, number 32 is the equivalent ASCII code of space, okay? The exclamation mark is the equivalent ASCII code of exclamation mark is number 33, okay? Double quotation, 34. The hashtag symbol or the sharp symbol, number 35, okay? So, if you want to use that, if you remember, there are times that we have to type enye. Okay, we have to type enye in the Word, Microsoft Word. Instead of inserting symbol, you can type what? Alt 164, Alt 165. So alt 164, 165 is the capital N, and then the small letter N. Okay? So that's how we use ASCII. It's the same with this one. If you want to type, you can try later on. If you want to type the sharp symbol, not using the key of key and the number shift number 3 for the number sign, you can type instead the alt 35. Okay? So for the percent, we have the 37. Ampersand, we have the 38. Okay? For example, I want to type capital letter A in the using the ASCII. I'm going to type Alt 65. Even in doing your program, if you remember, like for example, I want to do restrictions in a text box. Okay? So I want to use the key ASCII. Okay, and then I want the text box to accept only the characters capital letter A until capital letter Z. So I'm going to call the key ASCII values of 65 until 90. Have you done that before in your program since you are in your third year level? And aside from that, like for example, I want to use small letters only. Okay, so for my text box, I want to restrict my input. So basically, I'm going to call the key ASCII values of 97 until 122. Now, in my program, I want to restrict my input again. I want to use the format of numbers only. So for the numbers of 0 to 9, I'm going to call the key ASCII values of 48 and 57. Okay? So that's how you read the key ASCII. So here's the ASCII values of 0 to 9. As you can see here, I want to call the capital A to Z. Here are the key ASCII values. And I have the small letters A to Z from 97 until 122. Okay? So aside from that, it's like if you are doing your program, let's say you want to put some format, there are times that you are using the regex, right? You can also use the key ASCII. I want to do my format of, let's say, birthday. Oh, you can use the mass box, and then use the key ASCII and call what are the acceptable characters in your text box. Okay, so just be familiar with the ASCII table. You don't have to memorize this actually. You can download it, but if you want to memorize, it's easy to memorize because for 0 to 9, I just have to memorize key ASCII 48 to 57. Okay, for A to Z capital, I just have to memorize from 65 to 90. And then small letter A, 97 until 122 for the small letter Z. Okay? So next, text, images, and sound. In the same way that we code text, we can code virtually anything. An image is basically a rectangle of dots, and each dot is of a certain color. The color of these dots can be represented by a number. So I think maybe the best example here is that as you can see in the first sentence, we code text, we can code virtually anything. If you have done your program since first year, and then you're using a text-based programming platform like C, Turbo C, okay? It's a text-based program. You don't have graphics, so all you can see is text. And then you want to create a rectangle. You want to create a triangle. You want to create a heart. What can you do? You can just you're just going to code using the Gotok C, and then you're just going to use the period symbol. Depends on what symbol do you want to use, but you can form shapes, right? Okay, sound may be represented as a sequence of numbers indicating how to move a speaker. Moving to the next slide. So, history of computers long ago. So, we all started with the abacus, the legendary abacus. Okay? So, actually, this is an example of a Chinese abacus because there's a lot of type of abacus. Okay? Now, in the abacus, there are 2 beads at the upper part and there are 5 beads downward. So, mostly the abacus is used for what? This is used for computing. But what type of computing? It is used for counting, okay? It is used for addition, subtraction, multiplication, division, and even square root, okay? So that's beads and rods to count and calculate. So it still, although we have computers, abacus is still used, okay? Especially in Japan, they are using the abacus. So the next is the slide rule. Are you familiar with the slide rule? So slide rule in 1630, based on Napier's rule of for logarithms, used until 1970s. So this how slide rule looks. It looks like a ruler for me actually. But this one is used to compute for trigonometric functions, okay? So if abacus is used for addition, subtraction, multiplication, division, and square root, this one is used for trigonometric functions and logarithms or log, okay? It can be also used in square roots also, and even cube root, okay? Next, 19th century, we have the Jacquard loom. So Jacquard loom is created by Joseph Jacquard in 1801. So first stored program metal cards. First computer manufacturing, still in use today. So this is this composed of multiple punch cards actually, the Jacquard loom. So created for, of course, for looms, for creating looms. That's why it's called as the Jacquard loom. Next, so if Jacquard loom is created 1801, we also have Charles Babbage from 1792 to 1871. So difference engine, huge calculator that has never been finished. Also the Analytical Engine in 1833, which could store numbers. Calculating mill, use punch metal cards for instruction. Powered by steam, accurate to 6 decimal places. So actually, the Analytical Engine was inspired by the Jacquard loom. It was Charles Babbage inspiration. So this is the Analytical Engine, okay? That's the example of that's the how Analytical Engine looks like, okay? Next, the next one is the vacuum tubes. So 1941 to 1956, this is the first generation electronic computers use vacuum tubes. Vacuum tubes are glass tubes with circuits inside. As you can see, it looks like a valve. It looks like a valve, right? And then vacuum tubes have no air inside of them, which protects the circuitry. Next is the Univac, 1951. It's the first fully electronic digital computer built in the US. Created at the University of Pennsylvania. ENIAC weighed 30 tons, contained 18,000 vacuum tubes. Imagine. So it costs a factory of $487,000. It's too expensive. So that's how Univac looks like. See the big machines. Okay? Okay? So Grace Hopper, this is Grace Hopper, program Univac, recipient of the Computer Science First Man of the Year Award. So the first computer bug was identified 1945. Relay switches part of computers. Grace Hopper found a moth stuck in a relay responsible for a malfunction. Called it debugging a computer. So that's the history of debugging. Okay? It started year 1945. Okay? So next is the first transistor. It uses silicon, developed in 1948, won a Nobel Prize, on and off switch, and second generation computers use transistor starting in 1956. So from vacuum tubes, they use the transistors. Next, second generation, 1965, 1963, 1956, computers began to incorporate transistors. They replaced the vacuum tubes with transistors. So from vacuum tubes, the vacuum tubes is replaced by the transistors. Next, integrated circuits or IC. The third generation computers use the IC chips. IC's integrated circuits are transistors, resistors, and capacitors integrated together into a single chip. So from transistor into integrated circuit. Operating system, software. Of course, if we're talking about operating system, we're talking about software. Instruction for computers. Operating system is a set of instructions loaded each time a computer is started. Program is instructions loaded when needed. So the components of a computer system is of course what? We have the hardware, we have the software, we have the peopleware. Okay? Enable for the hardware to work, you need the software. Because without the software, how does the hardware works, right? And then, of course, who will use those computer? Who will use the hardware? The peopleware, us. Now, for the software, if you remember, there are types of software. We have the system software and the application software. When you say system software, we're talking about what? Operating system. And then, if we're talking about application softwares, what are the application softwares? Microsoft Office, Adobe Photoshop, okay? So those are the examples of application software. So third generation, we have 1964 to 1971. So integrated circuit, operating system, getting smaller, cheaper. So the first microprocessor in 1971, the Intel 4884, it was supposed to be the brain of a calculator. Instead, it turned into a general purpose microprocessor as powerful as ENIAC. So it had 2,250 transistors, 4-bit chunks, or ones or zeros, 108 kilohertz, called microchip. So what is a microchip? A very large integrated circuit, or VLSIC, transistors, resistors, and capacitors. So 4004 had 2,250 transistors. Imagine. And then Pentium 4 has 42 million transistors, each transistor 0.13 microns. Okay, so I actually used the Pentium 4 before. Did you naabutan niyo pa ba yung Pentium 4 before? Ano na ba naabutan niyo? Ako naabutan ko pa tong Pentium 4. So, fourth generation, 1971 present, microchips, getting smaller and smaller, but we are still using microchip technology. So the birth of personal computers. So the personal computers started year 1975. So MITS out there, 256 byte memory, 2 megahertz Intel 8080 chips, just a box with flashing lights. It cost 395 kit, 495 assembled. So next, so to summarize the generation of electronic computers, so we have first generation, second generation, third generation, and fourth generation. So for the first generation, we have the vacuum tubes. Second generation change into transistors, and the third generation change into integrated circuit, which composes of multiple transistors. And the fourth generation is microchips, which composes of millions of transistors. Okay? So the size of the vacuum tubes filled the whole buildings, while the transistor filled the half a room. The third generation is smaller, which is the IC, and the fourth gen microchip's tiny palm pilot is as powerful as old building size computer. Okay, so this is to summarize the discussion before. Over the past 50 years, the electronic computer has evolved rapidly. Connections, which evolved from the others, which was an entirely new creation. The vacuum tube, the IC, the transistor, and the microchip. So evolution of electronics from vacuum tube into transistor, into IC, into microchip. So the vacuum tube is a dinosaur without a modern lineage. A dinosaur because it's too big. Transistor, integrated circuit, microchip. So IBM PC 1981. So that's how an IBM PC looks like. The system unit lies down and then the monitor is above it. Okay? So IBM, Intel, Microsoft joint venture. First wide-selling personal computer used in business. So 8088 microchip to 29,000 transistor, 4.77 megahertz processing speed, 256 K RAM or random access memory standard, 1 or 2 floppy disk drives. Okay? I'm not sure if you encounter the floppy disk drives or the 3.5 floppy, if you remember, or the 3 1/4. It's a box type like a smaller, it's a box type that uses for storage. So next is the Apple computers, founded 1977. After Apple II released 1977, widely used in schools. So Macintosh released in 1984, Motorola 68,000, microchip processor, first commercial computer with graphical user interface and pointing device or mouse. Okay? Next, okay, so this is the, just to summarize again, the computer progress. We have the Univac, we have the MITS out there, we have the IBM PC, we have the Macintosh, and we have the Pentium 4. So for the Univac, the circuit is integrated circuit. It's out there. They use the two Intel 8080 microchip. The IBM PC used the Intel 8088 microchip. And then the Macintosh used the Motorola 68000. And the Pentium 4 used the Intel P4 microchip. While the RAM for Univac is 512K, the MITS out there has a RAM of 265 bytes. IBM PC has a RAM of 256 kilobyte and the Pentium 4 256 MB. Okay, and then the speed, as you can see, we also have the storage. So storage, we have the hard drive for the Univac, we have the MITS out there for the floppy drive, IBM PC, and then the Macintosh is also floppy drive, while the Pentium 4, this time they have the hard drive, they have the floppy, they have the CD-ROM. Okay? And then the size of each Univac is the whole room, the MITS out there, a briefcase, no monitor. And then the IBM PC, briefcase plus monitor. The Macintosh, 2 shoebox. Okay? And then the Pentium 4 is small tower. Cost, Univac is $1.6 million. The MITS outer costs $750. The IBM PC costs $1,595. And the Macintosh is $4,000. And the Pentium 4 costs $1,000 to $2,000. So it's getting cheaper. But the technology is, of course, much better. Next, 1990s, the Pentiums and the Power Macs. Early 1990s began the penetration of computers into every niche, every desk, most homes. Faster, less expensive computers paved way for this. Windows 95 was the first decent GUI for PCs. Macs became more PC compatible, easy file transfer. Price have plummeted from 2,000 for entry level to $500. 6,000 for top of the line to 1,500. So 21st century computing. Great increases in speed, storage, and memory. Increased networking, speed in internet, widespread use of CDRW. Okay, so we also have the PDAs. We have the cell phone or the mobile phone and then the PDA. And of course, 21st century is about wireless technology.